Hello guys, and welcome back to Introduction to Number Theory. Now we will discuss a very important property of Euler's function. Let me just remind you that Euler's function is the number of positive integers less or equal than n and mutually prime with n. It is called the Euler's function of n and denoted by phi of n. And the property I would like to discuss now is that if n is equal to n1 multiplied n2, where n1 and n2 are mutually prime, which means that their greatest common divisor is equal to 1, in that case, Euler's function of n is equal to such product. You see that it's equal to Euler's function of n1 multiplied by Euler's function of n2. So this holds only in case n2 and n1 and n2 are mutually prime. This is a very important condition. So let's consider an example. Well, say 15. 15 can be decomposed into 3 multiplied by 5. So 15 is equal to 3 multiplied by 5. We understand that 3 and 5 are mutually prime. So according to this statement, Euler's function of 15 will be equal to Euler's function of 3 multiplied by Euler's function of 5, which is actually true because Euler's function of 15 is equal to 8 and Euler's function of 3 is equal to 2 and Euler's function of 5 is equal to 4. You can check these numbers on your own. 8, 2 and 4 are the values of Euler's function of 15, 3 and 5 correspondingly. Okay, so this property is called multiplicity. The function for which this property holds is called multiplicative. So we say that phi is multiplicative function because this property holds. Now, since we stated it, we should prove it. I will show you a proof based on the mathematical induction method and using the amusing formula which we discussed earlier. So let me remind you that amusing formula says that n is equal to sum of values of Euler's function for every divisors of n, for every divisor of n, and also this holds for n1 and n2. Let's write here n1 and say that n1 has divisors denoted by d1 and n2, and with number 2, has divisors denoted by d2. So we say that it is equal to the sum of values of Euler's function of these divisors. Where may I remind you that n itself is also a divisor. So here in this sum, somewhere in there is phi of n also. And also this holds for n itself. And now, suppose that this statement holds for all numbers less than n. Well, mathematical induction method says that we can suppose that some statement holds for all numbers less than n. If it helps us prove that it holds also for n, then the statement is true. Of course, we need to check the basis, but in this case, it's trivial. Okay, so now we suppose that for every number less than n, this holds. Well, I suppose you understand what this means, but let me say it in words. This means that if we take another number, say not n but m, and m is decomposed into product of two mutually prime numbers, m1 and m2, so we simply substitute n with m everywhere, then phi of m is equal to product of phi of m1 and phi of m2. So and this holds for every number less than n, but n itself is kind of a riddle, so we don't know if it's true for n or not. And we're about to prove this using that it's true for all numbers less than n. Okay, so this is mathematical induction method. And let's now begin. Well, we take these two equalities and multiply them. So n1 multiplied by n2 is equal to, well, I'll just write it, and I think I don't need to read it. You can see it for yourself. So nothing outstanding so far, but let's notice right away that this thing here is simply n. Well, because n is equal to n1 multiplied n2. But what can we say about the right-hand side? Well, it can be expanded into the sum of all possible products for all possible pairs d1 and d2, where d1 is the divisor of n1 and d2 is the divisor of n2. Okay? So it's actually simply the distribution law. What next? Well, notice here that it looks very familiar, and it looks just like the right-hand side here. Every such product where d1 is less than n1 or d2 is less than n2, which means for all these products except for one of them, where d1 is exactly n1 and d2 is exactly n2. So all these products can be transformed, let's write it this way, can be transformed into phi of product d1 multiplied by d2. Well, of course, in order to state this, so we state that they are equal. In order to state this, we need to explain why d1 and d2 are mutually prime. It's obvious because d1 is a divisor of n1, d2 is divisor of n2, n1 and n2 have no common divisors except for have no common divisors greater than 1, which means that their divisors themselves must be coprime also. So we can substitute every such product with phi of d1, d2, except for one case. Except for the case where d1 is actually n1 and d2 is actually n2. So let's write this in another way. I'm laughing because this formula, it looks awful. It looks very strange, but it simply means, let me just finish the formula. This simply means that we take all possible pairs of divisors of n1 and n2, except for one pair where d1 is equal to n1 and d2 is equal to n2. And this specific pair, we just remove from the general sum. We just remove it, and it's just a separate summand over here. So what are we going to do with this now? Well, let's return to the beginning. It all began with n1 multiplied by n2. This is equal to n, and we know that n is equal, let me write it here, n is equal to, well, the same formula. Let's simultaneously take a look at this formula here, this expression here, and this expression here. Well, what do we see? First of all, d is a divisor of n. d1 is a divisor of n1. d2 is a divisor of n2. But n is equal to n1 multiplied n2. Does this ring a bell? Well, actually, it's easy to prove, it's easy to understand that every divisor of n is actually can actually be decomposed into product of divisors d1. Every divisor of n can be actually decomposed into products of two numbers, d1 and d2, such that d1 is a divisor of n1 and d2 is a divisor of n2. And this representation is unique. This decomposition is unique for each d, which is divisor of n. This means that this sum over here, this expression over here, and this expression over here are almost the same. They have many common summands. To be more precise, all these summands are included in this sum over here. I mean, any summand I take over here, I have the same number, the same expression over here. Because d1 multiplied by d2, this product is obviously one of the divisors of n. And every divisor of n can be decomposed into such product of divisors of n1 and n2. So, are these expressions the same? Well, not quite. This part of this big expression is fully included into this sum. But there is one summand here that is not present here. I think you understand that d1 multiplied by d2 can be anything but n. It is a consequence of this condition here. N would be, we would have gained n if we would taken d1 equal to n1 and d2 equal to n2. But since here at least one of them is not equal to n, then we don't get n here. So we understand that almost all summands here are covered by this sum. All but one. Which one? Well, of course, it's, let me write it here. Let me write it even more further. It's phi of n. Well, if we simplify this equality, and all this is an equality, let's just take a look. This sum is equal to n, it's equal to this product, is equal to this product, is equal to this great sum, which is equal to this expression over here. And now we notice that this sum over here and this sum over here are really have very much in common. And if we just remove all the extra summands, if we just remove all the summands that are the same here and here, on the left-hand side, this one will remain, and on the right-hand side, this one will remain. But since they are equal, it follows that the number that was left on the left-hand side is equal to the number that was left on the right-hand side, which proves that Euler's function is multiplicative.